So at the end of chapter 11, we talked about nociceptive chronic pain. The example was like a spine tumor pressing on or oversensitizing nociceptors, and it's ongoing pain because you have an ongoing biological source of pain. So the nociceptors are acting as they should. There is a source, there's something wrong, and they're responding to it. So the only way you're going to change somebody's chronic nociceptive pain is by getting rid of the source. So in this section, we're going to start to talk about chronic neuropathic pain, where the nervous system is actually affected. So for the learning objectives, I want you to be able to define the following, these are all symptoms of neuropathic pain: paresthesia, allodynia, dysesthesia, secondary hyperalgesia. We talked about primary hyperalgesia in chapter 11, and central sensitization. I want you to be able to describe the early and late stages of complex regional pain syndrome, which is one of the pain syndromes we will discuss. I want you to list the factors that contribute to chronic low back pain syndrome. I want you to be able to compare the signs and symptoms of the different types of headaches: migraine headache and episodic type tension headache, as well as chronic whiplash-associated disorder. And I want you to be able to describe the signs and symptoms and pathology of fibromyalgia. So we'll talk about all those things. So this idea of chronic pain as disease, rather than disease causing pain, the pain is the disease itself. So pain involves inhibitory and excitatory circuits in the central nervous system that either diminish or amplify pain messages. So that's the pain matrix we were talking about in the last section, and the anti-nociceptive and pro-nociceptive systems, and sort of the balance between the two. So when you have chronic pain as disease, neural mechanisms for regulating pain are amplifying pain signals. So rather than having pain because you have noxious stimuli, the neural mechanisms for regulating pain are actually creating pain in the absence of noxious stimuli. And you can also have pain matrix dysfunction and then certain pain syndromes that result from these basically neural changes. So pathological pain has no beneficial biological function. So nociceptive chronic pain does have a biological function in that there is something causing nociceptors to be stimulated, and the effect of that has to be taken care of to get rid of the pain. Pathologic chronic pain, neuropathic chronic pain, has no beneficial biological function. So the International Association for the Study of Pain defines neuropathic pain as pain arising as a direct consequence of a lesion or disease affecting the somatosensory system. So the somatosensory system is not normal. There are people who have the genetic codes that produce less of enzymes that regulate the levels of catecholamines and encephalin, and those people are twice as likely to develop neuropathic pain as those who produce more of that enzyme. So you could have a genetic predisposition to neuropathic pain, which is unfortunate, but there you go. So everybody responds differently to pain, and when we have neuropathic pain, it's almost a function of neuroplasticity. It's the changes that occur in our nervous system in response to some of these other things, like different enzyme levels or different things that result in pain. And we'll talk about individual pain syndromes in that light. So the symptoms of neuropathic pain are as follows, and I want you to know these definitions. A paresthesia is a painless, abnormal sensation in the absence of nociceptor stimulation. So a lot of times people describe paresthesia as something, it just feels weird. It feels wrong. It feels numb. It feels tingly. It's not necessarily a pain. It's just an abnormal sensation. We're not getting any stimulation of nociceptors, but we're getting weird sensations. Dysesthesia is an unpleasant abnormal sensation that's either evoked or spontaneous. So a dysesthesia is can be caused by nociceptor stimulation, or it can just arise spontaneously. Allodynia is pain evoked by a stimulus that normally would not cause pain. So if you were to brush someone lightly with a cotton ball, for example, and it's really painful, that would be allodynia. Secondary hyperalgesia. So we talked about primary hyperalgesia, where the nociceptors are sensitized and they respond to things that normally wouldn't be painful. Secondary hyperalgesia is excessive sensitivity to stimuli that are normally mildly painful in uninjured tissue. So in Tests and Measures Lab, we did the sharp, dull discrimination test. So that sharp point might feel mildly painful, like ow, but it's excessive sensitivity. So in primary hyperalgesia, the nerves are sensitized. You might feel things that you wouldn't have felt before. In secondary hyperalgesia, it's like it's turned up to 11. You have excessive sensitivity to stimuli that are normally mildly painful. So in the example that I gave before for primary hyperalgesia, where the person after knee surgery, it's uncomfortable to have, like blankets or sheets touching the area around their incision or their pants, above them. It's just uncomfortable. With secondary hyperalgesia, it would go into the point of being excessively sensitive, where it would be like, 8 out of 10 pain, or something like that. So it's like you turned primary hyperalgesia up to an extreme amount. So there are 4 mechanisms that produce neuropathic pain that we're going to talk about. And that's the list, but I'm going to go through each one individually. So ectopic foci, ectopic means an area that is, what am I trying to say? It means it's coming from an abnormal location. So when myelin is damaged, signals from the exposed axon can stimulate excessive production of mechanosensitive and chemosensitive ion channels. So remember, our ion channels in our neurons are being refreshed every few days. We're building new ones. So when you have damage and nervous system stimulation going on, we're producing different receptors. So it's producing more excessive production of mechanosensitive and chemosensitive ion channels. The channels are inserted into the demyelinated membrane, producing abnormal sensitivity to mechanical and chemical stimuli. So the demyelinated regions take on new pathological role of generating action potentials, in addition to the normal role of conducting action potentials. So now our nerves are hypersensitive because we have these new locations with newly sensitive ion channels that are then potentially generating action potentials. Ephaptic transmission is also called crosstalk. It's basically like a crossed connection where nerves are getting stimulated where they wouldn't normally be. Again, it occurs in demyelinated regions from injury, and probably occurs as a result of lack of insulation between the neurons. So one neuron gets stimulated and it can actually stimulate the one next to it because of that lack of insulation. Central sensitization is excessive responsiveness of central neurons, so not the peripheral neurons, but the central ones. It normally develops in response to ongoing nociceptive input, but the alterations in central neural activity outlast the tissue injury. So the original tissue injury and nociceptive input actually cause neuroplastic changes in the central nervous system that then create pain activity that outlasts the tissue injury. So that's that person that fell down the stairs in 1972 and they still have pain. The tissue injury is long since healed, but they still have the central sensitization that's causing them pain. Intense signals from an injury in the periphery may cause central sensitization. So that's one of the reasons why we focus a lot on pain control and pain management, is because we don't want an acute injury to develop into chronic pain. Cellular changes that reflect central sensitization include increased spontaneous activity, meaning the nerves are firing when there's no input. Increased responsiveness to afferent input, so you get a little bit of input and a lot of output. Prolonged after discharge in response to repeated stimuli, so that's again little input and a lot of output. And expansion of receptive fields, so where that nerve might have been sensitive in its original receptive field, now a larger area is sensitive for that same nerve. Oh, one more. Structural reorganization is where prolonged sensitization leads to rewiring of connections in the central nervous system. So in the dorsal horn, and I alluded to this a little bit at the end of chapter 11, structural changes include withdrawal of C fiber axon terminals from central nociceptive neurons. So you're not getting the C fiber input into those nociceptive neurons. Now you're going to form new synapses from fibers that produce impulses that are now going to be perceived as pain. So maybe you're going to take some of those A beta impulses from light touch and some of those other things, and they're going to synapse with those central neurons that used to be connected to the C fibers, and now even mild sensation is going to be perceived as pain. So that's the structural reorganization part of it.